Third law of thermodynamics. Third law of thermodynamics deals with the entropy of a pure crystalline system at 0 Kelvin. So, entropy of pure crystalline system at 0 Kelvin. That is at absolute zero. The scientists who were contributed to develop third law of thermodynamics are T.W. Richard, Walter Nernst, and Max Planck. Third law is based on the research works of these three scientists. A third law of thermodynamics overcome the drawbacks of Gibbs-Helmholtz equation. Overcome drawbacks of Gibbs-Helmholtz equation. According to Gibbs-Helmholtz, delta G, change in free energy delta G, equal to delta H plus T dou delta G divided by dou T at constant pressure. We can only use Gibbs-Helmholtz equation for some certain circumstances. That leads to the existence of third law of thermodynamics. So now move on to the details of third law of thermodynamics. In 1902, the scientist Richard studied the thermodynamic changes of galvanic cell and he concluded that at very low temperature delta G value becomes equal to delta H. That is, when temperature approaches a very low value, the Gibbs free energy will equal to the enthalpy change. So his findings can be write like this. Then limit T tends to 0, delta G equal to delta H. And later Nernst extended his conclusions. So according to Nernst, at very low temperature or at absolute zero temperature, not only delta G value becomes equal to delta H, but also their value approaches 0. So according to Nernst, limit T tends to 0, dou del G divided by dou T at constant pressure equal to limit T tends to 0, dou del G divided by dou T at constant pressure, and these two will be equal to 0. And this is known as Nernst heat theorem. This is known as Nernst heat theorem. And this theorem is particularly for pure solid substances. So this is for pure solid substances. We can define Nernst heat theorem. For a pure crystalline system, delta G and delta H become equals to each other and attain 0 when temperature approaches 0. Temperature approaches absolute 0. That is, limit T tends to 0, dou delta G divided by dou T at constant pressure equal to limit T tends to 0, dou delta H divided by dou T at constant pressure equal to 0. According to Kirchhoff law, so this term will be equal to delta S. According to Kirchhoff law. dou delta G divided by dou T equal to S. And according to Maxwell's equation, this term, that is dou delta H divided by dou T equal to Cp, del Cp. This is according to Maxwell's equation. So, from this we can say limit T tends to 0, S delta S equal to 0, when and limit T tends to 0, delta Cp equal to 0. So from Nernst heat theorem, it is clear that when temperature reduces or temperature approaches a very low temperature, the entropy of the system become equals to 0. And here limit delta Cp equal to 0, that indicates that the heat capacity, the difference in heat capacities of the products and reactant equal to 0. And graphically, Nernst equation can represent it like this. Here temperature, delta G value approaches and attains a 0 value. Same time, this is for delta G, and at the same time delta H also increases and comes equal to delta G value, and at very low temperature these two becomes same. And the scientist Planck extended Nernst equation to liquids also. So according to Planck, the entropy of a system, entropy of a liquid or a solid at absolute 0 is 0. So according to Planck's limit T tends to 0, S equal to 0. And the explanation he given for the statement is based on the statistical equation for entropy, that is S equal to K ln W. Here S is entropy and W is the probability of distribution. Probability of distribution. And the explanation was, when a system is at absolute 0, it is at 0 Kelvin, the substance occurs crystalline state. The substance occurs crystalline state. So for a crystalline substance, the probability of distribution W equal to 1. Hence, S equal to K ln 1 and ln 1 equal to 0. So S equal to 0. That is, we can write it as limit T tends to 0, yes, delta is equal to K ln 1 equal to 0. So this is the Planck statement. So from all these findings we can say, for every system, change in entropy delta S is always greater than 0, but at 0 Kelvin or at absolute 0, delta S will be equal to 0 for a crystalline system. So third law of thermodynamics can be stated like this: every system has a finite positive entropy, but at absolute 0 of temperature, the entropy may become 0 and does become in the case of pure crystalline substance. So let us calculate entropy of a system by using third law of thermodynamics. So entropy calculation. Entropy, change in entropy ds of a system is equal to change in heat energy divided by the temperature at that particular time. If we consider the entropy change at constant pressure, then we can write it as dSP equal to dQP divided by T. So let us differentiate this equation by using temperature. So we'll get differentiate with respect to temperature, then we'll get ds divided by dt at constant pressure equal to 1 by T dq divided by dt at constant pressure. So from thermodynamics, we know dq divided by dt at constant pressure equal to Cp, right? Heat capacity at a constant pressure. So dq divided by dt at constant pressure equal to Cp, heat capacity at a constant pressure. So we can rewrite it as ds divided by dt at constant pressure equal to 1 by T Cp. Now I am going to bring this dt term here, then I'll get ds equal to 1 by T Cp dt. Okay. Consider temperature of the system is changes from 0 to T. At the same time, entropy of the system will be changes from S0 to St. Here, S0 is the entropy at temperature 0. Temperature S0 is the entropy at absolute 0, and the Sc is the absolute entropy of the crystalline substance at a temperature T. So if we differentiate this equation ds equal to 1 by T Cp dt, then we will get integral 0 to S0 to St ds equal to integral 0 to T Cp dt divided by T. Here we will get St minus S0 equal to integral 0 to T Cp, and 1 by T dt can be written as d ln T. Normally the entropy at the absolute 0 will be equal to 0. So simply we can write this equation as St equal to 0 to T Cp d ln T. So from this equation we can draw a graph like this by plotting ln T value in x-axis and Cp value on y-axis. We will get a graph like this, and the area below this curve gives the entropy value. Practically we can only calculate the entropy up to 15 Kelvin. We cannot calculate the entropy at absolute 0, but we can extrapolate this curve and can calculate entropy value at absolute 0 also. So practically we can calculate up to 15 Kelvin. Okay. And by dividing this area into small pieces, we can calculate entropy, change in entropy in each sections. Okay. And the entropy change below 15 Kelvin can be calculated with the help of d by T cube law. So this law helps to calculate the entropy change below 15 Kelvin. Normally the absolute entropy at a temperature T will be equal to, we can split the area into simple parts and calculate the total entropy by taking sum of the individual values. Okay. So for example, St equal to 0 to T star Cp dt divided by T plus integral T star to T Cp dt divided by T. So just imagine that T star is a value in between 10 Kelvin and 15 Kelvin. So according to Debay's T cube law, we can take this term, that is the term below 15 Kelvin, the heat capacity in this term below 15 Kelvin, the heat capacity at constant pressure Cp approximately equal to Cv, and it will be equal to AT cube according to Debay's T cube law. And here we are taking T star, so this can be written as T A T star Q. Okay, so finally we can write this as, this term can be changed into 0 to T star A T cube dt divided by T plus integral T star to T Cp dt divided by T, right? And here this term, when we integrate this term, we'll get x will be T cube divided by T means T square. So we'll get, we can, first of all we can take constant A out, and this is T square. So T square, integral T square dt equal to T cube. Integral x raised to n dx equal to x raised to n plus 1 divided by n plus 1. So here t raised to 2 plus 1, that is 3 divided by 3, plus integral t star to t Cp dt divided by T. So this is the general equation to calculate the entropy change of solids, liquids or gases. So let us take an example. So the question is, calculate the entropy of solid methyl ammonium chloride at 298 Kelvin. Usually the solids exist in three forms: alpha, beta and gamma. In the case of methyl ammonium chloride, its transition is like this: beta to gamma to alpha. So for methyl ammonium chloride, from 12 Kelvin to 220 Kelvin, usually it exists as beta. And at 220 Kelvin, its transition occurs from beta to gamma. That is, from 220 to 264, it is in the form of gamma. And above 264, that is from 264 to above 298, this exists in gamma form. So first of all, we have to calculate the entropy change in each form of methyl ammonium chloride. Then finally, just we have to add the individual entropies. That's all. So the steps we are using to calculate the entropy in each steps is integral, simply integral Cp dt divided by T, right? Or we can say this integral Cp d ln T. Okay. So first of all, for methyl ammonium chloride, we have to calculate the entropy from 0 to 12 Kelvin. And it can be calculated by using Debye T cube law. So let it consider as delta S1. This is the value from 0 to 12 Kelvin Cp d ln T. Same way, from 12 Kelvin to 220 Kelvin, consider this is delta S2, that is 12 to 220 Cp d ln T. Same way, we can calculate the entropy change from 220 to 264 Kelvin, and it is delta S3, and 264 to 298 Kelvin, consider it as S4. Okay. The entropy of the solid at 298 Kelvin, entropy of the solid at 298 Kelvin is the total, is the sum of all these values. That is, it is equal to delta S1 plus delta S2 plus delta S3 plus delta S4. So same way we can calculate the entropy of liquids and gases also. The entropy calculated from third law of thermodynamics is called thermal entropy. Thermal entropy. So thermal entropy S equal to integral 0 to T Cp dt divided by T. And the entropy calculated by using Boltzmann equation, that is S equal to K ln W is called statistical entropy. This is statistical entropy. The thermal entropy and the residual entropy of a same system are not equal. Thermal entropy is less than statistical entropy. So some systems which shows lesser thermal entropy than their statistical entropy are water, nitrogen monoxide, nitrous oxide, N2O, CO, etc. That is, if we consider CO system, carbon monoxide, we are considering that the distribution, probability of distribution W of CO is 1. But actually this is not 1. Two such different arrangements are there. The statistical entropy is not equal to 0. So the statistical entropy little bit greater than thermal entropy. And the difference between the statistical entropy and thermal entropy is known as residual entropy. So residual entropy is the difference between statistical entropy and thermal entropy. So this is an exception to third law of thermodynamics.